Should I get another stapler to help out?
Yeah, that might be good. that might be helpful because they're, I'm almost done with the homework because you saw the last. Is that all for? Okay, I think that was all for homework. Yeah.
Printer issues?
What?
Printer issues?
Probably.
Yeah.
Oh, sweet. Thank you. Yeah, we got homework right there in the labs. Right there.
Well, thank you for doing that.
No problem. Thank you anyways.
Yeah.
What's the oh, that's the last page?
Yeah.
Gotcha. I'm just not used to the journal article being like the last one. Printer issues? Just not
I'm retarded. Just one of those days.
Nah, I get you.
All right. Awesome.
Last one.
All right. Thanks so much for the help.
Yeah, no problem. Thank you so much.
All right. I got the lab for you guys and the homework. So thank you guys for stapling. I forgot to hit the button. So yeah, go and grab those. I feel it. Oh yeah, I don't know.
You're getting some paperwork up too.
Feel the face I made.
More acids.
Yeah, we're gonna be dropping
My space.
You're the one who tried to like circle around and just kind of
I was doing a line, bro, a line. Oh, I forgot to grab you. Dang it. Look at you.
All right, let's talk about some announcements and just like things on the calendar. And so it's kind of come to our attention, and so this is kind of like us as the math science department, since we share a lot of the same students. But the problem is the way that the block scheduling has kind of worked out is it ends up being that it's like you can't attend any of the activities that we do. So for example, like it's come up, right, Earth Day, which you have people in the club for Earth Day or the co-presidents. And so I'll put out the date, sorry. So it is April, I don't know why I put two L's in April, 22nd from 11 a.m. to 2 p.m. But I understand that probably most people can't come to that because y'all are in classes anyways. And so I completely understand. But then I was looking at the radar. And so we have coming up, this is a while, so now this is in May 21st that I'm looking at. And from 11 a.m. going until 2 p.m. is World Day. And that's obviously during our class. So I kind of think that that would suck if you have to miss out on it. So then I was kind of thinking, well, what could we do as a class to celebrate World Day so that we could do a class World Day? And so kind of my best thought to incorporate cultures and science would be like liquid nitrogen ice cream teams. And so like I don't know if you guys are interested, so of course, we wouldn't have class, but instead as a class, what I would say is, if you guys like the liquid nitrogen ice cream idea, I would say, make culturally relevant ice creams, so you could make, I don't know, Mexican flavored ice cream, matcha ice cream, whatever. It doesn't have to be culturally relevant, just call it whatever, right? S'mores, that's good old American s'mores, whatever, right? Doesn't matter, however we want to sell it. You can make flag ice cream in colors, whatever. Just throwing out ideas, but I would say get teams of 3 to 4 people, make a batch of ice cream, so just something milk-based, roughly, and we can get into the details of how to make ice cream. But then we can, all table as like a class, and then we'll obviously bring liquid nitrogen and make a bunch of ice cream, right? Hand out ice cream, and then we'll be celebrating culturally and scientifically. So what do people, is that something that people want to do and make ice cream and form teams? I see some people really excited. So yes? All right, it feels like everybody is down. I think it's a Tuesday. So yeah, it would be a Tuesday. If we have to do adjustments to the quiz schedule, that's okay. That's too far out for me to think about our quizzes and assignments. But I at least want to put together that we're doing ice cream teams, so you can start talking about that and thinking about what ice cream you want to do. And that way we can participate in World Day. You get to finally do something, and then we can call it, class and activity. Sweet. All right, so that sounds good. So we'll put that on our radar. So we'll have ice cream teams, and probably not go to class that day. We might still have lab though, because I'm not sure if we want to cancel a lab day. So we probably just cancel class and then still have lab is what I'm thinking. So probably still. Well, we have other labs to get through, like making aspirin. I have to look at the syllabus. But yeah, we got to make aspirin. We got to. All right, so we'll put that on the calendar. So that's in May, so you guys can do some of these fun activities that RCC has. Because that's supposed to be part of community college, too, is getting to do the activities and building culture. All right, any other announcements or things we should talk about? All right, so let's get into our topic. And so we can think back to first quarter of chemistry, right? And I should have prepared better. But we can, of course, now think about all these solubility rules. And so if you kind of remember, right, they almost felt hand-wavy, right? We're like, well, they're kind of soluble, slightly soluble. These are our magic formula rules. But now what we're actually going to do is actually quantify this and bring numbers and actually figure out, well, how much can we dissolve, and figure out, right, the relevance of that. And so that's the first kind of line that we start off with, is so all ionic compounds dissolve in water to some degree. And of course, right, we established with our solubility rules, though, that some compounds have such low solubility that they are classified as insoluble. So we'll kind of put, right, solubility rules. And so, right, again, those rules just kind of seem to come from nowhere, and we don't really quantify them, and then they're kind of fuzzy and don't always agree. But again, it's just because we're not quantifying it. So now we want to quantify it. And so now we're going to be looking at, of course, some of those salts with really low solubilities, and we'll be applying our same concepts of equilibrium. So we're still going to be doing Rice tables, essentially. It's just now we're going to be looking at our KSP and determining their solubilities. And so the next thing is, of course, to write out our equilibrium expression. And so of course, it's related to the solubility product constant, our KSP, so again, different equilibrium expression. And so of course, if we're just looking at some ionic compound, so metal plus whatever our anion, and then our little subscripts, of course, balancing the charges, then our dissociation, of course, is you make that many moles equivalent of N and M of our cation and anion. And then when we write our KSP product, then that means that we take it to the power of our subscripts. So pretty similar. And so we can, of course, practice with our lead chloride. So we remember, right, we said with our solubility rules, that's insoluble. But now we need to quantify that. And so we start off by writing, again, it's a dissociation expression. So for every 1 mole of lead chloride, we make 2 equivalents of chloride, 1 equivalent of lead. And then our equilibrium expression, again, taking our chloride to the power of 2. This is SP, like how much is soluble. So, right, this is going to be our quantity, right? So how much is actually in solution. And we're about to talk about this relationship to molarity. And so this is just for reference, because we'll have to go back to this table, because I think your homework too makes a lot of comments like, oh, refer to the table, refer to the table. So here's a table of a lot of KSP values. And I believe that Wikipedia would also have them, so let's check that out. So yes, indeed. So I just pulled up silver chloride just as an example. And oh, I scrolled too fast. So there's the KSP from Wikipedia, so 1.77 times 10 to the negative 10. And then it also gives the solubility, so we could convert this to molarity. This is just given right in micrograms per 100 grams. And so that's the weird thing about like Wikipedia or looking up solubilities is that it gives it in random units. So just kind of watch for that. But then let's keep looking at this. And so now the next question is, well, we want to be able to kind of compare solubilities, right? Figure out which one is going to dissolve more particles at a particular temperature. So let's look at how we compare them. And so we're given this formula, and this is nice, but I actually don't like using the formula, so you can go ahead and write this down, but this is our direct relationship between molarity and KSP. And so you can see, right, it's KSP over our subscripts, right, so N to the M times M to the M gives you N, and then you take the whatever root of N plus M is, so this would be the third root for our lead chloride. But again, this feels pretty non-intuitive to me, and so we're going to kind of figure out how to rederive this as well. Again, you're more than welcome to use this relationship, but we can still use our Rice tables. And so this is kind of the key issue that we're starting to get at is, okay, they're related to KSP, but our KSP values of compounds cannot be compared directly, right? So for our KSP values to be compared, the compounds have to have the same dissociation stoichiometry. So all this is meaning, right? So we can't compare, oh, that's a bad example, but we can't compare, let's just take silver chloride versus lead chloride. So we can't compare those KSP values directly, right? Because this disassociates to 2 particles. And our lead chloride, we said disassociated to 3. So we have a little issue there. So that's where our molar solubility is useful. And so that's why we might want to go back and forth between the two, and that's very common where you're trying to figure out your molar solubility or determine KSP from molar solubility. All right, so now we want to look at our first example problem. So calculate the molar solubility of our lead chloride in water. And of course, let's look up our KSP value. So where's my chart? So lead chloride, according to this chart, is 1.17 times 10 to the negative fifth. And so then, just like before, we can set up kind of our Rice table with our reaction. And so we're just looking at our dissociation reaction. So lead chloride plus 2 equivalents of the chloride anion. And so then we want to start writing out kind of what we're calculating, kind of our reaction. And this is not included, right, in the solubility expression, but I'm going to kind of put S here in parentheses, because this is going to be our molar solubility that we're getting at, right? So we want to figure out, well, how much lead chloride is soluble. And so this is going to be equal to, so whatever this molarity is, we make S equivalents, right? And then we make, since of course we made 2 times as much chloride, we made 2S. So I just want to pause there for a second to make sure everybody follows so far. Is there any questions or anything? Does it make sense? And so just like before, we're going to plug this into our KSP expression. And so we said, well, our KSP then is equal to our concentration of lead times our concentration of chloride squared. So don't forget that squared. And so now you can probably see where this is going. So now we're going to plug in our values. So S times 2S squared. So now we solve. So then 2 squared is 4, so S squared, so this is 4S squared times S. So 4S cubed is equal then to our KSP, so 1.17 times 10 to the negative fifth. And so just keep solving, right? Algebra at this point. And then this is the answer I got for S, or molar solubility. So then, right, this is our molarity, so moles per liter. So 0.0143 molarity. So is that what everybody got? And then what did you notice, though, about this? Did this look maybe?
That's what the equation would have given you.
Exactly. And so personally, I don't like this equation. I don't know why. It doesn't click with my brain. So I like, kind of writing it out and rederiving it. But I totally get that you may not want to do that every time. Or maybe you just want to double check yourself. And so now let's plug it into our formula. But I think you'll see pretty quickly that it comes out. So we said, what? Yeah, I agree. The formula is kind of scary, but so right, we said our formula for molarity was N plus M, right, square root KSP over N to the N times M to the M, and that was for lead chloride, right? So then this is, so we'll just say N is 1, M is 2, right? So now this scary formula becomes way less scary, so molarity equals, so N plus N, so there's our cube root factor. And then, of course, 1 times 1 is 1, and then over 2 to the 2, so 4. So yes, that's exactly what we got from our Rice method. So again, whichever one feels best for you, you're welcome to use. I'll probably continue to use a Rice method just because a Rice method is helpful when we go to our next step. So we'll preview real quick where we're going. But the next thing we'll do is the common ion effect. So that's where you might want to do the Rice table. But all right, let's do another little practice then. And so let's compare, right? So I said, let's compare then. So find our molar solubility of silver chloride then. And so again, I'll put what our KSP was, so 1.77 times 10 to the negative 10. So go ahead and try that now for a second. And again, you can use the Rice method. You can plug it into the formula, whatever feels better. So I'm just going to start writing out the Rice method. And again, you could have plugged it in. That would be fine. I'm just showing, so our ions in solution, and then our solubility that's not counted. And then, of course, this time write S and S for 1 equivalence each. And then plugging into our KSP. So now it's just silver times chloride. So that gives us S squared once we plug it in. So 1.77 times 10 to the negative 10 equals S squared. And then formula should have given you the same thing. So then did we get that number for our molar solubility?
So does that tell us that silver chloride is a lot less soluble than chloride?
Exactly. So,
Smaller number, like less moles dissolved.
yep. So, right, did everybody hear that? So now we can compare. So just to recap in case. So now we can see, right, we have a 10 to the negative 5th molarity that can dissolve. So that's pretty small compared to, right, our 0.0143 molarity for our lead chloride. So yeah, right, the conclusion is that our silver chloride is even more insoluble than our lead chloride. All right, let's keep looking at this. So now we have our common ion effect. So again, kind of similar to what we were thinking about with our weak acids and weak bases, right? And what happened when we added our common salt. And so like you might expect, if we add a soluble salt, so now let's kind of think about this example here. So we can think about our lead chloride. And then what happens if we add sodium chloride to this? And so we can use Le Chatelier's principle. And so what do you guys think would happen? So right, it shifts to the left, and then if it's shifting to the left, right, then it means that more of our solid is going to form, so it's more insoluble. And so now, right, we can quantify this. And so let's calculate, so what is the molar solubility then of calcium fluoride if our solution contains a 0.1 molar solution of sodium fluoride? And you probably want the KSP. So calcium fluoride is 1.46 times 10 to the negative 10. So see if you can try it on your own, at least the setup, and we'll walk through it. For the calcium fluoride, so this is a KSP. So you want to use your rice table. And so to start off by writing out the dissociation reaction again. And so, right, we can use, use our rice table. So we have our initial conditions, right? So it's nothing is in there except for 0.1 molarity of our sodium fluoride. And then, of course, right, our change would be figuring out, again, with our S molar solubility, well, how much will be dissolved, right? So then that's figuring out how much plus S and plus 2S. Then that gives us our equilibrium. So of course, right, again, this is not included in our equilibrium expression. So just trying to emphasize that. And then S, 2S plus 0.1 molarity. So did we get to here for our setup? That looks good. Just kind of pause here for a minute, give people a second. So this is, right, good. Should feel hopefully repetitive. Not always the most exciting part of chemistry, but hey, you got to quantify stuff. And this would be important, you know, if you want to go into more like chemical engineering and designing things, or like, you know, because what they're working with is different vats of solution. How do you change that concentration? How do you get out impurities? So all that kind of goes with our solubility, at least all those fundamentals. And so again, just like before, we can do our math. So set up our KSB expression. So our value is equal to, of course, our calcium times our fluoride squared. So don't forget that. So now I'm just plugging things in. And so this, at this point, does anybody have a guess what we're going to do at this point? Yep. So we're going to make an assumption. And again, our hint is that we have a very small KSP, so 10 to the negative 10. So that means we're going to ignore this 2S, right? Because we're going to assume that this 0.1 is much, much larger. So that helps us with the math. And again, if you want to plug this into, you know, a Wolfram Alpha or other math calculator, you just note that, show your work. And so just continuing on, so now we're at, so 0.1 squared then times S is equal to and so just algebra. So then we get this number for our molar solubility. And so I guess it'd be a good question to now say, let's compare. So what's our molar solubility of calcium fluoride then normally? So see if you can calculate this now. Again, Rice method or formula. So now we can see the effect of adding in that ion. So what do we get for our molar solubility? So I'm kind of working through it, not using the formula. But any answers while I punch this in, or guesses?
I got one, I'm not sure if it's right or not, but I got 3.32 times 10 to the negative 4.
I also got that.
So that sounds good. So let's see what I get. You said 3.32. Yep, times 10 to the negative 4. Perfect. And so that's kind of interesting to me. So now we can kind of zoom out and appreciate. So just adding, right, that 0.1 molarity of our salt. So looking at our scenario, so right, we added that 0.1 molarity of sodium fluoride, and then that reduced our molar solubility all the way down to 10 to the negative 8, so that's kind of crazy, molarity, versus its normal solubility of 10 to the negative 4. So that's just kind of cool to me as well. Questions on this what we just did, either our molar solubility with our common ion, or calculating this again? Oh, there's a question on wine. And so I think, so the question is, I think they're just confused over where our concentration of fluoride comes from in this example. But we have to think back to Le Chatelier's principle, right? So because we added our sodium fluoride, right, we added our 0.1 molarity of fluoride, right? So then that influences our solubility. And so we can either see that, right, with Le Chatelier's principle. So we said, okay, with that common ion effect, so we would have the same thing with calcium fluoride, right? Add fluoride ions in, and it shifts it back to calcium fluoride, so making it less soluble. And so we're not really getting the concentration of fluoride ions right from calcium fluoride. So this is already in there, and then our change is accounting for how much gets solubilized from calcium fluoride. All right, I think that clarified it. So let's look at kind of the next thing, kind of where we're going. And so we can also see the effect of pH on solubility. And so I was debating whether to bring this in or not, or if we should play around with this in lab. And so let's first look at this before we talk about what we could play with. And so we have, for insoluble ionic hydroxides, the higher pH, the lower the solubility of the ionic hydroxide. And so what this is saying is that if we're in a higher pH environment, right, so then that's saying, well, high pH means greater concentration of hydroxide, then you're going to have a lower solubility of whatever ionic hydroxide that is. And so that makes sense, right? And so let's look at that. So again, same thing, let's talk about specifics now. So usually people like to talk about magnesium hydroxide and calcium hydroxide. So these are both two pretty insoluble hydroxides, and you can kind of play with them and figure out the pH. But first of all, let's look at what this scenario is saying. So again, it's saying, of course, right, we have our dissociation. So it makes hydroxide. And so this is basically the common ion effect that it's saying. Well, if we're already in an environment with a lot of hydroxide, again, it's going to shift that equilibrium back. And obviously, these hydroxides won't be as soluble. And then, of course, right, they make this passing comment, right, the lower the pH, the higher solubility. And so now that depends if it's so acidic, right, then it's actually being consumed. And so we could say, right, so with acidic conditions, then you have to think about that hydroxide, or any hydroxide, right, reacts with our acid, of course, to do our neutralization. And that in turn is, of course, removing hydroxide.